Hi, I'm Byeongkeun at Korea University, and I'm going to present our work, Invertible Monotone Operators for Normalizing Flows, a new normalizing flow with monotone operators. Normalizing flows, or NFs, are probability densities built by transforming tractable densities like Gaussian into more complicated ones using learnable diffeomorphisms. However, they are subject to two constraints. They must be invertible, and the Jacobian log determinant must be evaluated efficiently. So, it remains a challenge to design expressive architectures satisfying the constraints. To satisfy them, many architectures adopt special structures which limit their expressivity. An alternative is resonance-based NFs, which impose no restriction on the network structure. However, to ensure invertibility, they constrain the Lipschitz constant instead. This restriction is still significant since transforming between distributions requires a large Lipschitz constant. In this work, we address the Lipschitz constraint while retaining the architectural flexibility of resonance-based NFs. But how? To get some intuition, let's review resonance-based NFs in 1D. As resonance, they take the form fx equals x plus gx, but g should be a contraction mapping to ensure f is invertible by applying the Banach fixed point theorem on the right-hand side shown in red for each y. However, notice that f can be invertible when g is not a contraction. If gx equals 5x, g is expansive, but fx equals 6x is invertible. Why? Because f is an increasing function. In fact, every resonance-based NF is an increasing function since f has a slope lower bounded by a positive number. We can generalize this argument to higher dimensional spaces by defining monotonicity using the dot product. Then we have roughly the same property as in 1D. Now, how do we parameterize monotone operators? We utilize the geometric property of monotone operators. When their graph is rotated 45 degrees counterclockwise, they become one Lipschitz operators and vice versa. This operation is called taking the Cayley operator. Therefore, we parameterize the Cayley operator in the same way resonance-based NFs parameterize their residual branches since both are one Lipschitz. To be explicit, if g is an L-Lipschitz function, we define fx as shown here, and the inverse takes a similar form. For training, we use the usual maximum likelihood objective. Backpropagation through the inverse function follows the previous work. The log determinant adopts a slightly different form, but it is still amenable to Taylor expansion and stochastic approximation as in the previous work. We also propose a new activation function, Concatenated Pila, to improve the gradient flow. For theoretical analysis, we compare our monotone formulation ML with two baselines, the residual formulation RL and the inverse residual formulation IL. First, IL is equivalent to RL multiplied by a constant. Second, ML is equivalent to a constant times R 2L over 1 plus L squared, which is strictly larger than L. Third, ML includes but is not limited to RL and IL. We visualize in the right figure the expressive power as how much the function value can change compared to the change in the input. Our ML has the greatest expressive power. For experiments, we first fit a staircase-shaped function that has a large Lipschitz constant. We can observe that ML in D performs the best, while RL in B and IL in C perform comparably in agreement with our theory. Second, we test our model on 2D toy datasets. Our model improves upon the baseline in all datasets. Finally, we evaluate our model on image density estimation. We achieve better bits per dimension values than comparable baselines. To sum up, we presented an NF based on monotone operators, which is architecturally flexible while bypassing the Lipschitz constraint. We proposed a new activation concatenated Pila to improve gradient flow. Theoretically, we proved that our model is more expressive than the baselines. Finally, we validated our model's performance on toy and image datasets. Thanks for listening.